So now we move away from the realm of the kinds of things that we've been seeing for the past 8 chapters into chapter 9, solids and fluids. We start looking at the states of the matter, and then understanding deformation of solids, looking at density and pressure, variation of pressure with depth, where we start dealing with submersing things and determining what types of pressures we're dealing with. Pressure measurements, buoyant forces, and Archimedes' principle. And then we move to fluids and the fluids in motion, other applications of fluid dynamics, surface tension, capillary action, viscous fluid flow, transport phenomenon. So in this section, this chapter, we start looking at defining matter as a solid, liquid, or a gas. All matter is classified as being in one of these 3 states. Solids has a definite volume and has a definite shape. A brick has a volume and a shape. Liquids have a definite volume but no shape. A liquid takes on the shape of its container. A gas has no definite volume and no definite shape. A gas will continue to expand as long as you let it go. All matter consists of some distribution of atoms or molecules. Atoms are held together electrically by a charge, and they vibrate about an equilibrium position. As energy is added to a material, the amplitude of the vibrations increases. A solid is said to have elasticity. So if you think about putting something in the microwave. When you put something in the microwave, the heating action is based upon the energy being applied and increasing the vibrations of the atoms or molecules in the material. And that's what actually cooks anything that goes in the microwave. Solids and liquids have a property in common. When an attempt is made to compress a solid or a liquid, strong repulsive atomic forces act internally to resist this compression. And we're going to see this is the effect that occurs when you use a hydraulic pump or even the fluid in a syringe. In a gaseous state, molecules are in constant random motion and exert only weak forces on each other. Occasionally the molecules collide with each other, but most of the time they just kind of move around freely and randomly. All objects are considered deformable. If you put enough force or enough pressure on them, you'll be able to change the shape of the object. It may be minuscule, but you'll be able to change it. It's possible to change the shape or size of an object, or both, by applying sufficient external force. When the force is removed, the object tends to return to its original shape. Think about a spring. We take a spring, we put it into compression, and as soon as we let go, what happens? It tries to return back to 100% of its original shape. The object deformation then exhibits an elastic behavior. Elastic properties of solids then are discussed in terms of stress and strain. Stress is related to the force causing deformation. Strain is a measure of the degree of deformation, so one leads to the other. Elastic modulus is what we call the proportionality constant or stress of an object to strain. And there's a relationship then between stress and strain. This ratio then becomes, stress over strain becomes the elastic modulus. So if we look at an example here, we've got a bar of material here, and we're going to try to elongate it. Okay, we've got some cross-sectional area, we've got some force, and we've got a length and some change in that length, delta L. So we define the tensile stress as the amount of force divided by the cross-sectional area. So it's the ratio of force to area. Okay. Now we have a relationship that says 1 Newton per meter squared gives us a definition for 1 Pascal. Tensile strain then is defined as the delta length, the change in length, over the original length. No units because they cancel out. And Y is the tensile stress divided by the tensile strain. So if we take force by cross-sectional area and divide it by the change in length by the original length, we come up with a relationship of force times the original length divided by the cross-sectional area times the change in length. Okay. So we can see here, if we graph out what's going on here between stress and strain for a material, you can see the elastic behavior stays fairly linear until it hits some limit, and that limit is where deformation starts taking place. And you'll notice we've got a curve, and then we have some breaking point. If we want to define the shear modulus, the elasticity of the shape, we can see here, if we have one side anchored and we try to push on it, much like what they're showing here with a textbook. If you ground the book onto the tabletop and push on it, the top tends to move while the bottom stays put, okay? And you can see it's F sub S, so it's definitely defined as some friction. So as we try to move across the top of the material, we're going to get some change in the distance that the material moves in deforming here through the shearness, and we have a fixed height. Typically the height will reduce a little bit as this action occurs. So the shear stress divided by the shear strain, in this case force by cross-sectional area, the change in the distance that the top moves divided by the height. The last one, the bulk modulus, we've got a volume stress now divided by a volume strain. Okay, this is typically what you would think about taking a ball and putting it in the swimming pool and taking it down way deep. You're going to have a volumetric compression on all sides of the object. So the volume stress, delta F by A, then is equal to the volume strain, delta V, by the original volume. So we're going to define this delta F by A as the change in pressure divided by the change in volume as a ratio of the original volume. So we could take a quick look at an example here. A vertical steel beam in a building supports a load of 6 times 10 to the 4th newtons. If the length of the beam is 4 meters and its cross-sectional area is 8 times 10 to the minus 3 meters squared, find the distance the beam is compressed along its length. Okay, so we've got it all laid out here, all our dimensions, all of our information here. So Y of the steel then is equal to 2 times 10 to the 11th Pascal. Okay, that would be, Young's modulus would be something that you would look up in a table. So the Young's modulus of the steel then is defined by the relationships, as we saw, the force divided by the cross-sectional area, all of that divided by the change in the length by its original length. So we can move our terms around. We have force times length divided by cross-sectional area and the change in length. So now at this point, all I have to do is move my terms around. I'm going to be solving for the change in length. So I'm going to swap places here. Y steel, the Young's modulus, with the delta L. And when I put my values in here, 6 times 10 to the 4th newtons, 4 meters, 8 times 10 to the minus 3rd meters squared, and 2 times 10 to the 11th Pascal, I come up with 1.5 times 10 to the minus 4th meters is the amount of change that I get in the length of the steel beam, okay, going into compression. Then what is the maximum load in newtons the steel beam can support before falling? So we break this apart from the table again. The ultimate compressive strength of steel is 5 times 10 to the 8th Pascal. So force by area gives me a value of that I can set equal to 5 times 10 to the 8th Pascal. Okay, so I'm going to be able to determine my force from this relationship. So when I multiply 8 times 10 to the minus 3rd meters squared times 5 times 10 to the 8th Pascal, I get 4 times 10 to the 6th Newton meters squared over meters squared. The meters squared cancel out, and I'm just left with the force, 4 times 10 to the 6th Newton. So for the sake of safety, this is the minimum value. The true value would be a factor higher during the design. So these guys, when they're doing their designs, would know, okay, as a minimum, 4 times 10 to the 6 newtons of force would be our minimum. Okay, so when we come back, we're going to take a look at arches and the ultimate strength of materials.